In this video we'll look at once again parametric equations, but in relation to motion along a straight line where we have a velocity and we have time, so therefore the parameter t would now always be positive. So we have looked at this before, and once again if we have a starting position at x0, y0, we have a direction vector which is now our velocity. We can work out a parametric equation in terms of the x and y component, and we'll get x0 plus at, y0 plus bt. Once again, time cannot be negative, greater than or equal to 0. The speed of this motion is the length of our velocity vector, so the square root of a squared plus b squared. Also notice that the velocity vector, if you differentiate x, you'll get a, differentiate y, you'll get b. So x dash, y dash gives us our components for our velocity vector. Alright, example question here. Once again we have x and y as our equations. Notice these are linear expressions. That's why we have a constant velocity, time greater than 0, distance in meters. So if we were to work out our initial position, then we need to let t equal 0. So we work out x of 0, we'd end up with 2, and we work out y of 0, we end up with our value of 4. So if I were to plot that on my Cartesian plane, we have x equals 2 down here, y equals 4, and there is our starting point. The velocity vector is from the multiplier of t. In each case it's going to be negative 3 and 4. If you differentiate x, you'll get negative 3, and differentiate the y, you'll get the 2. So negative 3, 2 is our velocity vector. Illustrating the motion, I need to work out the position at t equals 1, 2 and 3. So just substituting 1 in place of t, we end up with our next point. So the point would be negative 1 and 6, takes me up to there. Substituting t equals 2 in each of the x and y values, we get our next pair of points. So at negative 4 and 8, so up at that point there. And when t equals 3, and likewise we get our final point at negative 7 and 10. Now notice that if we were to look at the change in the x values, these values here are going down by 3 each time. It's a constant change. Whereas the y values, these values here, are going up by 2 each time. So that is our uniformly changing situation. Alright, next working out the speed. The speed is the length of the velocity vector. So I can do that by squaring the x component, y component, adding them together, and we have units here of meters per second. Alright, part E, working out the Cartesian equation. Once again I need to rearrange one of these two equations to make t the subject and substitute into the other. So I'm going to rearrange the x equation. I end up with x take 2 divided by 3. If I now substitute that into y and then expand, collect and simplify, there is my Cartesian equation, and that's in the form y equals mx plus c, which is the equation of a straight line, as our graph did show us. Right, once again you can do this on your graphing calculator. If I go into graph mode once again and make sure we have the right type, so parametric, I've entered these two equations in here. If I now draw that, I get my straight line graph. Once again if I go trace, I've changed the pitch to 1, so now if I push across, now push across to the right here because t is getting larger, so t equals 0, push across, t equals 1, t equals 2, 3, and so on. So that is how you use the calculator to draw this motion.